Good afternoon, everyone. I'm Zhou. I'm from Yale School of Medicine. Today, I'm going to share our recent work, DPAdapter, a collaborative effort with colleagues from Indiana University, Zhejiang University, and Stanford University. So I want to provide some background first. In a typical machine learning scenario, like during the model training process, particularly with deep learning, it is really crucial to recognize that the training data itself might contain some sensitive or private information. So because deep learning is basically a data-hungry algorithm, it tends to memorize the training samples. So without implementing a robust privacy protections, there exists a significant risk that attacker could extract this information from the model parameters. So in an effort to safeguard training data, previous work has focused on differential private machine learning, DPML, as a means to address this challenge. Among the most notable approaches are differential private stochastic gradient descent, DPSGD, an optimization technique that offers a strong guarantee of data privacy under differential privacy. I know the previous talk is just give a brilliant introduction about what is a DPSGD, but for the sake of the integrity, I just gonna quickly go through what is the DPSGD in here. So the DPSGD method is straightforward. Imagine we want to train a deep learning model. We start by selecting a batch of data. Based on this batch and the loss function, the model would have a corresponding gradient represented here by a blue arrow. Next, we clip the gradient. This means cutting off those large gradient components to ensure each component can be bounded. Finally, after clipping, we add Laplacian noise to the gradient. This noise gradient meets the DP guarantee, which theoretically bound any privacy leak about the batch data from the gradient. So, however, DPSGD comes with its own set of challenge. One of the biggest issues is that it can significantly reduce the model utility, making it harder for model to perform well. On top of that, it often makes the training process more difficult and less likely to converge smoothly. Because of this challenge, using DPSGD usually requires carefully tuning and a lot of fine-tuning to get it just right. Therefore, our motivation is trying to mitigate those challenges. More specifically, our research question here is, given a relevant public dataset, can we first identify a starting point in a flatter loss landscape so that later the impact of adding DP noise on the gradient of batch private data, the loss won't shift significantly? Our motivation considers that the current popular MLOS, machine learning as a service supply chain. In this system, upstream model vendors create a pre-trained model using extensive public datasets. Then, downstream users fine-tune this model using their private dataset. Since it needs private dataset for training purpose, DPML can be deployed in here for private protection. Our motivation is to explore how upstream vendors can optimize the pre-trained process to enhance the effectiveness of DPML fine-tuning by downstream user. The goal is to achieve better utility with the same privacy budget. All right, so what's our solution? Overall, our method named DPAdapter contains 4 steps, quite similar fashion with the sharpness-aware minimization. The main goal of this entire process is to improve the parameter robustness of the pre-trained model, which is also known as the loss landscape. Essentially, we are trying to make the model parameter more resistant to noise. This is really important because in differential DPML, we are actually adding noise to the model's parameter on purpose. So if we can make the upstream model better at handling those noise, the upstream model better at handling the downstream task, especially when they are similar, they will benefit as well. Now let's break it down step by step. In our method, step 1, start with a warm-up by training with the training data for a few epochs. Step 2, next, calculate the worst case perturbation. Select the B1 samples as the batch data needed to calculate the perturbation. find a gradient update that maximizes the increase in loss for this batch of data, which is the opposite direction of the normal updates. This one creates the worst case perturbation and adds this perturbation to the model parameters. And it is important to know that B1 should be relatively large, which we will justify this in the theoretical part later. Step 3, then we select another batch of B2 samples needed for the update, optimize the perturbed model using this new batch. Step 4, similar to the most sharpness-aware optimization fashion, after optimizing, remove the worst-case perturbation added in the step 2 from the parameters and repeat the step 2 to step 4 until the model converges. So in the end, by using the pre-trained model we've developed, we can achieve better performance in downstream DPML tasks. Unlike most traditional DPML enhancement techniques that focus on optimizing during the DPML phase, our approach is focusing on the procedure before DPML phase. So this distinction makes our method more adaptable and easier to combine with existing DPML enhancement technique. So in the later of this presentation, we will show how this approach delivers such combination result. So how about our performance? We tested 4 different DPML methods, excluding DPSGD, and 4 different pre-trained methods on CFR 100, including training from scratch, normal pre-training, parameter robustness training from previous work is basically adding the random perturbation, and our method DPAdapter. In 3 different downstream tasks, DPAdapter consistently outperformed the model pre-trained with the vanilla method, shows improvement ranging from 3% to 16%. To further evaluate the impact of public dataset and the model architecture, we selected a variety of upstream training dataset and models to evaluate the stability and performance of DPAdapter across different privacy budgets. The number inside the box in here indicates the accuracy in the downstream task, which is fixed as STL10 dataset. This table showcases the impact of choosing between CFR 100 and Tiny ImageNet as our upstream training dataset, as well as the influence of different model architecture. Whether we are leveraging the sophisticated transformer architecture of VIT or the robust CNN framework of ResNet, DPAdapter consistently demonstrated its ability to enhance downstream DPML outcomes. Since DPAdapter optimized from unique angle, not from DPML phrase itself, but from the upstream, it naturally leads us to consider the potential for even greater result when combined with other DPML enhancement technique. Here we present one such combination by enhancing the pre-trained model with DPAdapter and pairing it with existing DPML enhancement technique, MGC, implement in the downstream. The combination effect of DPAdapter plus MGC surpassed the performance of using MGC with a standard pre-trained model alone, resulting in a 12% improvement on accuracy. So why DPAdapter effective? We are also looking for a theoretical understanding that can get future research. So in theory, we present 2 main theorems. First, theorem 1 established that under certain reasonable constraint, B2, which is the batch set used when computing the perturbation, is directly proportional to the upper bound of the model's convergence rate. This implies that a larger B2 is likely to lead a better optimization minimum. Second, theorem 2 provides a theoretical explanation for the effectiveness of DPAdapter. Starting from a point with higher parameter robustness, enable the DPAdapter, DPSGD to achieve a minimum with lower loss. In the end, I want to give some takeaway of this presentation. First, we will observe that a pre-trained model with better parameter robustness or so-called loss landscape can significantly enhance downstream DPML. Essentially, if you start point Your pre-trained model is more robust. It can set a strong foundation for the rest of your training. It's like building a house. If your foundation is solid, everything else you build on top will be more stable. Next, we investigated about the batch size when you compute the perturbation. So we have noticed that the batch size here has a significant effect on how well your model can optimize during training. With a larger batch size, you are essentially giving your model more data to process in each step, which helps it navigate the optimization process more smoothly. Last one, something really interesting here is that how parameter robustness of the pre-trained model can serve as an independent beneficial resource. This is above and beyond what existing methods usually focus on, which is mainly about fine-tune on the downstream task. So this additional robustness can give you a high start and can be a game changer, so particularly when dealing with sensitive data where private is a priority. To sum up, starting with a robust pre-trained model, carefully consider with the batch set and leveraging the extra robustness are all crucial strategies to get most of your DPML training. Yeah, thank you. That's all.